Yeah, so I could join from my Zoom application now. All right, so I think the internet fortunately has come back here.
Okay, good.
I have been able to join from my original device, which I planned.
Good, good. Welcome.
Yeah, that's good. Continue, okay.
Yeah, can you share your screen?
Yeah, I can share my screen. Wait a minute. Okay, so here I have shared my screen, and I hope you can see that.
Yeah, we can see.
Yeah.
And I am audible, right?
Yeah. Yeah. Sir, can we start?
Yeah, sure. Krishnendu, shall we start?
Yeah, so can you give me 1 minute? Just let me try to fix another thing, and then maybe in 2-3 minutes.
Yeah, please.
So I have some. Yeah. Okay, Somo. So we can start. No problem.
Yeah. Okay. Over to you, Rana sir. Yeah.
Just a minute. So let me welcome all in the meeting. Is my audio on? Yes, my audio is on.
Yeah.
Yeah. So let me welcome you all. And it's my pleasure to introduce the speaker for the event today. I welcome Dr. Krishnendu Gongopadhyay for this event. He is the main speaker for the today. He is Associate Professor at Indian Institute of Sciences and Science and Education, IISER, Mohali. He obtained his PhD from IIT Bombay, and his areas of interest are hyperbolic geometry and group theory mainly. Let me just mention some of the achievements. He has already published more than 40 research publications, guided 7 doctoral students, organized many workshops and conferences, and delivered more than 25 invited talks. He is also on the editorial board of Mathematics newsletter of Ramanujan Mathematical Society. With this short introduction, let me welcome Dr. Krishnendu and request him to start his presentation.
Okay, so I hope I am properly audible.
Yeah.
Yeah. Okay. So, so thank you very much to Professor Inder K. Rana and Soumya for inviting me to this nice activity. I really appreciate the work Professor Rana is doing. So as you have listened that I was a student of IIT Bombay, and Professor Rana was an inspiration from my student days. So it's really a pleasure for me to give this lecture in an activity which he is organizing. So now let me start with, I am not assuming any background in this lecture, and it will be meant for entirely to a general audience. So if there are participants who has some mathematical background and who may find it very elementary, then my apology. I mean, I saw the aim of this math clinic, and it seemed to me that it is for general mathematical awareness. So I have prepared my lecture accordingly. Now, I would rather say that instead of an introduction to non-Euclidean geometry, we can also call this lecture an introduction, an invitation to non-Euclidean geometry. But before I tell you what do I mean by non-Euclidean, let me revise what is our school geometry. So the school geometry is geometry of the world that we live in. So like on the land, we have beautiful architecture, we have homes, you have the laptop screen or the mobile screen to which you are listening to this lecture. Everything has a geometric shape. And this geometric shape is built upon the kind of geometric shape that we see in front of the screen now. You have triangle, you have rectangle, you have this rhombus, and there are several angles on a triangle, etc. Now, the discipline of mathematics that studies these shapes of several geometric figures, of several sort of construction figures, that calls a geometry. And the geometry that we are more familiar is the geometry which we learn in school. Now, what is the word geometry means? The geometry is a Greek word and it means earth measurement. Now, when you build up a structure, you have to measure several things like, you have to measure length, you have to measure angle, right? And the civil engineers, they have to measure it very carefully so that the structure of the building they are preparing, that should not collapse. And for that, precise measurement of several tools or several angles, several lengths, area, etc. are needed, right? And the branch of mathematics, which is called geometry now, studies properties of figures in space so that the precise measurement can be made. Now, much of the development of geometry is the result of efforts throughout many centuries to construct a body of logical doctrine to correlate geometric data obtained from observation and measurement. From ancient time, when human beings started building up engineering structures, which we see in our real world, I mean, you have this measurement of unit. Earlier, it was by hand or by some scale, by some unit, and then you also have measurement of several other shapes. Now you correlate all the data and you formulate a general theory so that one can study them systematically. And that was the reason geometry was started in human scientific history, because human being wanted to study the shapes of several figures in our real world by in a systematic way and in a logical way, and the evidence came from this observation and measurement. The kind of geometry that we see in the school is based on a text, a classical text. It's called the Elements of Euclid or the Euclidean Geometry. Now, who was Euclid? Euclid was a Greek mathematician who was likely to be born in 325 before Christ. Not much is known about his life, but the book is very famous because it's a kind of classical, very first doctrine of study of geometry, which was needed because Greeks were excellent in architecture, so they needed a systematic study of geometry. And what Euclid did, he essentially wrote them down in terms of books. So it is not clear how much originality Euclid had in his books, but it is definitely clear that it was a sort of well-defined subject in Greek history, and there were many mathematicians before Euclid who sort of studied geometry, and Euclid wrote all the existing ideas and theory in 13 volumes of books. And that 13 volume is the basis of our school geometry, which we call by Euclidean geometry. Okay, now Euclid and other ancient mathematicians who started this, they followed their evolution of the geometry was more philosophical. So they knew what ancient philosophers knew, that not everything can be proved. So to build a logical structure, one or more propositions or properties must be assumed, and the others follow by logical deduction. Now, which one to be assumed? So to begin with, you need to assume something. Now, which one to be assumed? So the things which are sort of universal based on our everyday experience, those are assumptions that we need to assume at the beginning of geometry or any mathematical area. Modern mathematics is based on some different kind of assumption, which is called axiomatic set theory, but our school geometry was based on our everyday experience of measurement and lengths, which we assume. Now there were 10 assumptions of Euclid. 5 of them are called axioms, and the rest are called postulates. Now axioms are common notions, the universal truths which we see every day. But postulates are assumptions specific to the study of geometry. Now before axioms or postulates, one need to define something. I mean, if any of you have happened to see the Constitution of India or any government booklet like the new education policy, you will see in the first few pages, they always define certain things because definition makes things precise. So Euclid also defined something. So he made 23 definitions at the beginning of the book before making the axioms. And a few of the definitions are like the following. Like, what is a point? A point is that which has no part. In modern term, if you take a pen, just put a dot on the piece of paper, that's a point of the piece of paper. A line is a breadthless length. The ends of lines are points, and a straight line is a line which lies evenly with points on itself. In other words, you take a modern scale and just draw a line along the scale, that's a straight line. Now, we will learn later that the straight, when you measure, when you have a measurement of a line from our everyday experience, you can say that the straight lines are the shortest line between 2 points. Now, here I am assuming that you can measure the distance between 2 points using our engineering tools like scale and compass, like that. But when Euclid started, he did not assume it. But for our understanding, you can now know that the lines are the shortest line between 2 points. The straight lines are the shortest line between 2 points. Now, a plane or a surface is one which lies evenly with straight lines on itself. So you take a collection of straight lines joining to each other, and that spans a plane or a surface. Now, if you look at these definitions carefully, these are not very well defined notions. Because there are terms like, part or breadth, which are not defined, which we do, when Euclid started, so he did not define what is a part or what is a breadth. But based on our everyday experience, we can think of them intuitively. And we can have an intuitive idea of what is a point. You put the tip of the pen on a piece of paper, that's a point. A line, you draw the pen along a scale, that's a straight line. A line is any zigzag kind of curve that you can draw on the piece of paper, something like that. So you assume these you know these definitions. Then what? Then Euclid made the axioms. And the axioms are again based on our everyday experience. like things which are equal to the same thing are also equal to one another. If equals be added to equals, the wholes are equals. If equals be subtracted from equals, the remainders are equals. Things which coincide with one another are equal to one another, and the whole is greater than the part. So these are axioms. These axioms are based on our everyday flat world experience. Like you take a geometric shape, if you call that as a whole, when you cut it up into pieces, then those parts are smaller than the whole. That's the fifth axiom. Now, if you take two equal shape, if you take one model shape, then anything that you can overlap with it, they are equal to each other. That's the first axiom, and so on. So these axioms refer to magnitudes of some kind that I have just mentioned, or to different shapes in the plane. So these are axioms based on our everyday experience. But now comes the postulates, which are very specific to this geometry. Now, here are 5 postulates of Euclid. So the first postulate is about straight lines, that you take any 2 points, you can always draw a straight line between these 2 points. That we can do, we know that we can do that. Now, you take any 2 points, you draw a line, a straight line joining the 2 points, then you can produce them infinitely. That means you can extend them as long as you want. So these are the 2 postulates about straight line. The next postulate is about another geometric shape that we see every day, that is a circle. So you have engineers, classical engineers have this ruler and compass. So you draw a round shape by choosing a center and then choosing a radius from your center to the perimeter of this round shape. So the curve that it draws, that's a circle. So circles, so that's the third postulate, that to describe a circle with any center and radius. That means you fix a point and assign a radius length, then you can draw a circle with the center P and the given radius R. So that's the third postulate. Then the fourth postulate is about angles. Now again, here we have no measurement, but in your physical life, when you construct a house, we see that there are angles at corners of our houses. All right, so here, for example, I have this envelope. Now this shape, when you have this vertical line and you have this slipping line, so when the slipping line and the vertical line meets to a point, then there is this nice shape, and that shape is the measurement of a right angle. All right, so this shape can be called as right angle, and all other part of it can be thought of as angles. Here I have not assigned any measurement to the angles, but just by looking at the shape, you can define what is the right angle, and then several parts of the right angle as other acute angles. So now here is the fourth postulate, that all right angles are equal to each other. That means whether I take this envelope like this or I rotate it, the right angles at this point will not be the same. So whenever you see that you have one standing line and one slipping line meeting each other, that's the right angle. And every right angle are equal to each other. That's the fourth postulate. It's a very important postulate. Now when you can measure the angle, you attach some measure, which in terms of degree is called 90 degree, but you can also attach a number to the angle, which will come shortly. But this is the fourth postulate, that all right angles are equal to each other. Now the fifth postulate. The fifth postulate says the following, that suppose you have 2 straight lines, like on the screen I have this straight line given by AB and CD. Now suppose you have another straight line which intersects these 2 straight lines, and the angle that it makes with these two straight lines on the same side, like at P and at Q, if their sum is less than two right angles, then the straight line, the two straight lines AB and CD must intersect at a point. Now, what is mean by two right angles? That means you have one angle and you have one right angle, you have another right angle, you join them like this. All right? Then the angle here, you can think of that as two right angles. So, as I told you that the angle here is a, sorry, not here, here, there are several angles and we can add angles. So when you add two right angles, that gives you, that you can think of like a line, right? The angle made at a line. So here it is saying that if these two angles, so when you have two straight lines and a line intersect the two straight lines, if the angles on the same side is less than two right angles, then the two lines must intersect at a point. Equivalently, for every line L and for every point P not lying on L, there exists a unique line passing through P and parallel to the given line L. That means you have a line and you take a point outside the given line. There can be one and only line which is parallel to the given line. That means these two lines never intersect. So this is called the fifth postulate of Euclid, or the parallel postulate. And this is one of the bases of our school geometry. Now, as soon as you assume this postulate, the famous theorem, so you have, what is a triangle first of all? So you take three lines, all right? Suppose the three lines intersect, so pairwise intersect each other at one point. Then you get a shape like this, ABC. That's a triangle, and it's a theorem in Euclidean geometry that the sum of three angles of a triangle is always equal to two right angles. So this is essentially the basis of Euclidean geometry, which tells us that the sum of three angles of a triangle is always equal to two right angles. Now, to prove this, one first prove the following, that suppose you take two lines L and M cut by a transversal line which is drawn here, and then this L and M are parallel to each other if and only if this alternate interior angles alpha and beta are congruent. That means you can, if you cut it along the along this line, and then you can actually overlap these two angle segments. So that's what congruence means. Now, as soon as you know this, then take a triangle ABC and take a line L which is parallel to BC. Now, by Euclid's fifth postulate, given a point A outside BC, there is this unique line L which is parallel to BC. Then, okay, can you see my this little hand? Oh, you can see it, right? Okay. So I have this line BC. Then I take the sum of two right angles. So here, this, as I told you, what is the sum of two right angles? You have these two right angles, you join them, right? So I say it again. So I have this one right angle, which is like this. I have another right angle like this. I join them along this common vertex. Then I get a line, and I assume that the angle here in this line is sum of two right angles. So here at the point A, you have the sum of two right angles, that is equal to this angle O plus angle B plus angle G. But now by this green colored statement, angle O is equal to angle B and angle G is equal to angle C. So the sum of angle A, angle B and angle C is equal to the sum of two right angles. So this is the theorem that the sum of three angles of a triangle is always equal to two right angles. Now, as a number, so far we have not attached any number to the angles. I have always urged you to think of the angle as a shape, that you have a vertical line and you have a slipping line. When they meet each other and like this, then that's a right angle. Now you can attach some number to measure the angle, which classically one did by degrees. So we call this angle as 90 degrees. So two right angle means 90 degree plus 90 degree, which is 180 degree. But degree is an integer, or maybe degree is a fraction of two integers. But when you have, so you start with a number system, 1, 2, 3, 4, like that, then you get fraction out of the number system. But later, mathematicians realized that there are numbers which are not fractions. Now, what is the number? So by number, you can think of something which you can add and you can subtract. Now, angles, we can add two angles, as we have done, and we can also subtract two angles. Like here, you can subtract angle, G plus B plus O. This is two right angle. From there, you can subtract angle O. So you can subtract angle. So angles should really be think of something like a number, and you can express every angle by a number, which now we call as real number. Now there is a real number which is denoted by pi, this symbol pi. Now what does it mean? That really means sum of two right angles. Alright? So now as a real number, pi has this nice property that you cannot express it as a fraction. You can only approximate it by a fraction. So its precise value by a fraction is never achieved. But that's a different story. For us, pi means the sum of two right angles. So this is essentially this sum of angle O, orange, gray, and green. So sum of these three angles, we define it as pi. And when you take its half, that's a right angle. All right. So with this, I think I am more or less done with the revision of our school geometry, which is called Euclidean Geometry. Now, this geometry is prevalent everywhere you see in your real world. You look at your houses, you look at your TV screen, you look at your mobile screen, everywhere the shapes are the kind of shapes that we see in Euclidean geometry, and the underlying engineering tools are also based on more or less Euclidean geometry. But in ancient time, most of the people used to stay in land, but there were some people who used to roam around. And the route they used to follow was the route of a sea, the sea route. So they used to take a ship and they used to travel. Now, while traveling, they realized that the kind of measurement they used to do in the land is somewhat not accurate when they travel along the sea. So they developed their own tools of measuring the distance between 2 points on the water route, on the sea route, and that was in terms of certain angle of a given star or the moon or the sun. Now, why the kind of measurement we do on the land, they realized that it is not exactly appropriate in the sea. Now, People understood it from ancient time, but now we know that it is because the shape of the earth is round. Now this sailors, so at that time, not everybody understood that it's entirely round shape, but they thought that earth is something like a bowl where the ball is placed on the reverse, ulta karke rakh diye hain, and the human being are on the flat shape and the stars etc. are on the upper hemisphere of the bowl. But later people realize that the earth is round, and this is the reason that what we are habituated in the land, the same measurement does not hold true exactly on the entire surface of earth. Now, few years back, I was going to Sydney from Delhi. Now, while going from Delhi, which is somewhere here, and Sydney, which is on the other hemisphere of Earth, in the flight they used to they were showing the flight navigation. Now, I was surprised to see that the flight navigation was something like this along the arrow route. Now, the question that one can ask is the following, that we just saw that when you take 2 points on the earth, the shortest distance is the distance between distance along the straight line. So the flight should have really taken a route like it will go up, and then it should have taken this straight line to Sydney. But it is taking this beautifully curved line which resembles part of a circle. It is also not taking a route like it goes from here to here, because when you go up, you have to go with a bit slope, and then it is not going straight and then again coming down. But it is always taking a route which looks like a circular route. Now, why air planes take such a circular route? Again, you can guess the answer, because the earth is spherical. Now, but then I understand earth is spherical, but then why not this route, but this route? To know the answer, we need to learn about a different kind of geometry, which is the global geometry of the round world. This geometry is different from what we learned in school, and this geometry is called spherical geometry. Now, it is almost as old as the Euclidean geometry, because the sky above us is spherical, and not only the sailors, but there were astronomers or the star observers who used to use this sort of measurement for measuring the movement of a star. Now, what are the basic objects in this geometry? In the school geometry, the basic objects could have been drawn by a ruler and a compass. But here we have one extra object, which is the sphere. Now, the sphere I am not defining here, but you can think of it like the following, that you have an axis and you draw a circle along the axis. Now, if you rotate the circle continuously, then the surface that it moves, that's a sphere. Or it is something like we see the sky along with our flat land, that's a hemisphere, and you add 2 hemispheres, that's a sphere. Now, on this geometry, the points and the lines are, you have to choose appropriately. Points are points, like Euclidean geometry, but lines, there is no straight line on a sphere. If you look at the earth, you never can draw, or you take a football, you can never draw a straight line on a football, right? So here the lines are replaced by great circles. Now, what is a great circle? A great circle is a circle on the surface of the sphere whose center coincides with the center of the sphere. All right. So it is like you take North Pole and South Pole, you draw a circle joining North Pole and South Pole along the surface of the earth, that's a great circle. Now, 2 points lie on the opposite side of the great circles are said to be antipodal. All right? So, the antipodal points are points which lie on the opposite side of a great circle. Now, each diameter, so if you think of the center of the earth, then draw a diameter along the center of the earth that hits the sphere at exactly 2 points. Now, those 2 points are antipodal points. So, these are the elements of spherical geometry. So, you have a sphere which is like the surface of a football. Then take a point on the football, that's the points. Lines are great circles, which you take any 2 points along the which are the opposite points of the diameter along the center of the football. Then draw a circle through these points. So those circles are called great circles. So in this geometry, we replace straight lines by great circles. Now, what about Euclid's postulate on the sphere? So the first postulate, the second postulate, and the fourth postulate, you keep them as it is. Now, there are some basic differences. So first of all, what is the angles at the point on a sphere? It's the same like Euclidean angle. What you do, you take 2 circular arcs, take a point, then draw 2 tangent lines through this point. Then the Euclidean angle they define, that's the angle at the point P, which is the intersection, which is this point, this intersection point of these 2 circular arcs. So that's the angle, and all right angles are congruent to each other on the sphere also. Now, a line segment, that means you take a circular, you draw a line on the earth, then you can produce it indefinitely. A line may be drawn from any point to any other point. So as I told you, we are replacing straight lines by great circles. So you take any 2 points, you can always draw a great circle passing through these 2 points. But remember, in the case of Euclidean geometry, you have 2 points, there is a unique straight line joining these 2 points. But on the sphere or on the football, you take 2 points, like I have this North Pole and this blue point. So there is one orange arc, which is the part of the great circle that is joining these 2 points. But there is also this yellow arc, which is the other half of the great circle that is joining these 2 points. So a line may be drawn from any point to any point, but unlike Euclidean geometry, this line is not unique. All right, so these 3 postulates are same as Euclidean geometry, but unlike Euclidean geometry, where you have a point and you take as large as you want radius, you can draw a circle. But in spherical geometry, there is no circle with arbitrarily large radius. All right, and finally, the parallel postulate breaks down, because in spherical geometry, my lines are great circles. You take any 2 great circles, they always intersect. So there is no parallel line in spherical geometry. Now, what about the sum of 3 angles of a spherical triangle? So you draw a triangle, so you take 3 great circles which intersect each other once, that encompasses this region, which I have denoted by red, 3 red circular arcs and named as PQR. So that's an example of a spherical triangle. Now you have angle at the vertices, which are denoted by alpha, beta, gamma. Then the sum of the 3 angles of a spherical triangle is always more than 2 right angles. Why that is so? Here I have drawn a schematic picture. So you take out this triangle on the bottom, PQR. Then you can always draw a Euclidean triangle passing these three points. Now we have already seen that the angle, the sum of the angles of the Euclidean triangle is more than two right angles. Sorry, the sum of the angles of the Euclidean triangle is exactly two right angles. So you still have some extra angle in the spherical triangle, which is outside this Euclidean triangle. So we conclude that the sum of the angles of a spherical triangle is more than two right angles. Now, if you attach this real number pi, then that means that alpha plus beta plus gamma will be more than the number pi, which means sum of two right angles. Now, unlike Euclidean geometry, here you have something more. We know that sum of three angles is more than two right angles, but can the sum be as large as possible? The answer is no. In spherical geometry, you take any triangle, then the sum of the three angles of a triangle will be less than the sum of six right angles. So the sum of the three angles of a spherical triangle ranges between two right angles and six right angles. And unlike Euclidean geometry, here triangles are nice because as soon as you measure the three angles of a triangle, that gives you the area of a triangle. So you just take the sum of the three angles, remove two right angles from the sum, that's the area of a spherical triangle. Okay, so this more or less gives us the geometry on the sphere. But now, so far, we have talked about triangles, we have talked about lines in spherical geometry, which are great circles, but how to measure the distance between two lines? In our flat world, we have the scale and the ruler and the compass, but how do you measure distance between 2 points on the sphere? Now, if you follow our ancient astronomer or ancient sailors properly, it's the same way you do. So by some sort of an angle, you measure the distance between 2 points. Now here, in modern term, what we do, you imagine that you take your football or the earth, you take the center of your football, or the center of the earth. Then the angle that the radius from C to P and C to Q make, that is the measurement of the distance between P and Q. Now, using this convention, the distance between any 2 points on the sphere is either zero, ranges between 0 to pi. So pi means two right angles. So it cannot exceed two right angles. The distance between 2 points on the surface of the sphere cannot exceed two right angles. And it is precisely equal to two right angles if and only if these points P and Q are antipodal points. All right. And you can check that the great circles, they give you the shortest distance between 2 points on the sphere. So in this geometry, we are also replacing our distance by a new scale, which is the scale of angles, and the great circles gives you the shortest path between 2 points with respect to this distance. All right, so this geometry is different from Euclidean geometry, but not entirely, because of the following. What is the earth? We know what is the earth. We live on the earth, right? And we assume that there is a sky which is spherical. And if you, so what is our sky? If you follow our ancient philosophers, so they will tell you that the sky is infinity. So that means anything which is not infinity belongs to the real world, and anything which is infinity belongs to the sky. Now, what is that infinity in terms of geometric term? So this picture will explain you what is infinity. So infinity is just a point. So what you do, you take a sphere, you think of your world, and take P as your north pole. Now, if you draw a line through the hollow area of the earth to somewhere in the sky, then that line will hit the surface of the earth at exactly one point q, and then it will hit another point q prime, which is a flat plane. So this way you can to every point other than P on the sphere, you get a point on the plane. You can think of the plane as what we lived in. So this plane, you can move it through the center of the earth, then you will realize that what I am saying is exactly the case. So that means a sphere can be thought of as a infinite plane, as a plane which has no end, and a point which is not on the plane. So spherical geometry is like our flat earth and a point which is not on our flat earth, which is somewhere in the sky, which is infinity. And this projection, so you can project sphere minus a point to a flat plane. And this projection has a name, it's called stereographic projection. It is an important projection that has been used historically. But the point here is that spherical geometry can be thought of as Euclidean geometry with an added point somewhere, which is not on the Euclidean plane. And there are certain postulates which are different here from the 5 postulates of Euclid. Of course, the parallel postulate is different, but there is one more postulate which is different from the, you see? So there are 3 common postulates between the Euclidean geometry and the spherical geometry, even though the first postulate is not exactly identical, but somewhat close, and the third and the fifth postulate are completely different. So it's a different kind of geometry to what we have seen in the school. But some modern mathematicians do not call it a full-fledged non-Euclidean geometry because of this projection and because they want something else. What they want is that they want to keep as much as possible postulates of Euclid as it is, and then they want to derive a different sort of geometry from there. Now, for that, we need a completely different kind of geometry. That geometry also we can get from our real world experience, and for that, you need to look somewhere other than the sky or the land. You have to look inside the sea. So there is this nice coral reefs inside the sea. So they are now endangered because of global warming, and it is important for preserving our nature to preserve them, but that's a different issue. If you look at this coral world, then the kind of geometry they exhibit, that's a model for the kind of geometry that is different from both Euclidean and the spherical geometry, but it exists in nature. But this geometry was not discovered until 200 years ago. And this is called hyperbolic geometry. So how it was developed? So there is a rich history of all these 3 geometries, which I am not expert, but here I am essentially trying to emphasize on the development of how how the ideas were developed. Now, how the hyperbolic geometry was developed. So people observed that Euclid did not require the 5th postulate to prove his first 28 theorems. Now this is strong. That means the 5th postulate was not essential to prove many of his theorems. But there are some theorems where 5th postulate was important, like the theorem we proved that the sum of the angles is 2 right angles. Now Euclid and many mathematicians thought that the 5th postulate is because of that that many results did not use the fifth postulate, Euclid and many mathematicians thought that the fifth postulate can be proved from the first four. And they started attempting that. Now all attempts to do that failed. Now people were trying it repeatedly, and every time people were failing. Either they were developing something which is again equivalent to the fifth postulate, or they were not developing something. So people were experiencing failure and again. But now, as they say, that failures are the pillars of success. Now all these failures that led to the success story of creation of the most satisfying non-Euclidean geometry, which is known as hyperbolic geometry. So when people started attempting to prove the fifth postulate from the first four and they could not do it, they started asking a different question. They started asking that you keep the first four postulates as it is and replace the fifth postulate by something else. Now what sort of geometry it will give you? So that's what they did, and that created the hyperbolic geometry. Now this is a geometry where you keep all the first postulates of Euclid unchanged and replace the fifth postulate by a completely different phenomenon from Euclidean geometry. You assume that given a line L and a point P not in L, there are more than one lines that pass through P and are parallel to L. So you keep the first four postulates as it is, replace fifth postulate by this one. Then can you develop a body of logical doctrine which is like Euclidean geometry but different from it? And people found that you can actually do it. And you can have different shapes in this geometry, and you can prove nice theorems using these five postulates. Now here I draw your attention to the fact that this is a very strong statement, because that you are keeping all the first four postulates of Euclid unchanged. That means any theorem in Euclidean geometry which is relying on the first four postulates remains true in hyperbolic geometry as well. And anything which uses the fifth postulate breaks down here. So including, we have seen that the sum of the angles of a Euclidean triangle is two right angles. Now here, naturally, when the fifth postulate is replaced, you can assume that the sum of the angles of a hyperbolic triangle cannot be two right angles. And it is indeed the case. Here, the sum of the angles of a hyperbolic triangle does not exceed two right angles. Now, to prove this, it requires some work, but for the moment, what I will do, I will assume that we know a hyperbolic. I will show you what are the hyperbolic triangles. You will see that they look like this green triangle, which is made of three semicircular arcs. And unlike spherical geometry, here a Euclidean triangle exceeds this hyperbolic triangle. So that sort of gives you the intuition that the sum of the three angles of a hyperbolic triangle must be less than two right angles, which is the sum of the Euclidean angles at PQR. But like spherical geometry, in hyperbolic geometry also, the sum of the angles can give you the area of a triangle. So you just compute the defect of the sum of the angles of a hyperbolic triangle, which is you take two right angles, subtract this alpha, beta, gamma from there. So that gives you the area of a triangle. Now, one of the remarkable property that hyperbolic triangle satisfies is that hyperbolic triangles are thin. From the picture, it is clear what thin means, but mathematically also, thin means that you take any point on a given edge of a hyperbolic triangle, there is a point on either of the other two edges that lie within a distance, which is a fixed distance delta, and it is true for any point. So you take any point on the edge PQ, you always get a point on either on QR or PR that lies in a distance which is less than this fixed constant delta. Delta has a value which I am not talking, but wait, I am talking about distance here, isn't it? Now, what is the distance in hyperbolic geometry? We have seen what is the Euclidean distance, which is the distance we measure using scale. We have seen what is the spherical distance, which is the distance. I mean, if you remove one point, you measure it by a scale. But if you think of it globally, you associate some sort of an angle with a point which is outside your sphere, either at the center or somewhere, and you measure the angle between these 2 points. That's the distance on the sphere. Now, what is the distance on a hyperbolic space? How do you get it? Now, using the concept of distance, like we did for Euclidean geometry, you can also define a distance in hyperbolic geometry. Now, again, I am remembering what are the tools we had in Euclidean geometry to measure distance. We had ruler, we have compass, we have protractor. And the distance between 2 points was measured along straight lines. Now, what you do in hyperbolic geometry, you cannot do the same because the fifth postulate has changed. So the lines cannot look exactly like straight lines. You have to replace your piece of paper by a different piece of paper, and you have to draw the lines differently. Now, what you do, you choose an appropriate piece of paper and then you scale the Euclidean distance in a suitable way. And what is the piece of paper? The rectangular piece of paper that you are habituated, you replace that by a circular piece of paper. So you cut a circle along the piece of paper, and then that circular piece of paper is now a hyperbolic plane for you. All right? Now, what are the lines? Any semicircle that is orthogonal to this boundary circle of the piece of paper, you think of them as your lines. So you replace straight lines by any semicircular arc which is orthogonal to the boundary circle, and also the diameters, because now, and the distance on this disk, which is the model for me for the hyperbolic space, is given by this ratio of the. So if you denote the Euclidean distance between 2 points by dpq, then the hyperbolic distance between 2 points is given by this quantity, but you have to take the image of this quantity by this cosine inverse function. If you don't know what is a cosine function, just forget it at the moment. So it's some function, and the hyperbolic distance, when you give an input into this function, give you this output, which is a appropriate fraction of the Euclidean distance between the points x and y on this disk. Because after all, you remember, we have cut our disk from the piece of paper where you draw Euclidean geometry. So Euclidean distance is still valid, but the hyperbolic distance is scaled by the Euclidean distance in this way. And my lines in this geometry are semicircles or the diameters orthogonal to the boundary circles. Now look at one fact. What about when, so this O is the origin and X is a point anywhere on this circular disk. Now when X approaches the origin, so you take a point X, when X goes towards the boundary, we can further assume that the radius from O to P is always 1. So we can assume that our model for the hyperbolic geometry is a disk whose boundary circle is of radius 1 and center O. Now when the point X reaches this boundary circle, this distance, the Euclidean distance between X and O, reaches 1. Now 1 minus 1 is 0. So what does it mean? That means if my X or Y approaches the boundary, then the distance between X and Y goes to infinity. Even suppose I fix my Y to be this point O. Then as X reaches this boundary circle, the distance from O to any point on this boundary circle goes to infinity. So what does it mean? That means the following. In Euclidean geometry, when you take 2 points, you can extend them as long as you want. But there is only one infinity. When you know spherical geometry, you know that that infinity is somewhere in the sky. And if you attach that infinity to your Euclidean plane, that gives you sphere. But in hyperbolic geometry, there is not a single infinity, but there is a whole family of infinity in the boundary circle. So the hyperbolic space is bounded by points at infinity, and the points of infinity is a circle. So you can reach infinity. So if you stay on a hyperbolic plane, you can reach infinity at all directions. All right. So that's what this formula means. And in the geometry, it is indeed the case if you make it more precise. Now, what are the triangles in hyperbolic plane? We have already announced that we will consider the semicircular arcs orthogonal to the boundary as our lines in this geometry, and the piece of paper is the unit disk. Then this black and white sets, they all represent triangles. And sum of the 3 angles of a triangle is obviously less than 2 right angles. But here there is something more. In Euclidean geometry, we have the notion of a similar triangle. Suppose you have 2 triangles, one is small, another is big. If they have the same angles, we call the triangle similar. But you cannot really overlap the small triangle to the big triangle. All right. So there is another notion which is called congruent. That means if 2 triangles, they have the same shape, they are congruent. But in hyperbolic geometry, triangles are always either congruent to each other or not congruent to each other. Now, that means this big triangle, look at my little hand. So this big triangle, this is congruent to this small triangle. This is congruent to one of these small triangles, and so on, which is pretty surprising. Maybe surprising to you, but you think of the person who is lying on the boundary. So they are lying at infinity, so they are like God, right? Which we think of God. So God are everywhere, right? So, and all are equal in the eyes of God. So on the boundary, from the boundary, whatever triangle you look into, relatively from our Euclidean eye, even they look bigger and smaller, but from the point of view on the hyperbolic space, everybody is equal to each other. Everybody is congruent to each other. So the 2 triangles, if they have the same angles, they can be either congruent to each other, or if they don't have same angle, they cannot be congruent to each other. There is no concept of similarity here. All right. Now there is one more thing in it. Recently, we have seen COVID-19 outbreak everywhere. And that's why I am giving you this lecture online. All right. So now look at the COVID-19 graph of India. So from 26 June to March, the growth of COVID-19 pandemic was more or less uniform with time. So such sort of growth is called linear growth. But after 23rd March, with the same unit of time, the graph was increasing very stiffly. And you know by this time that that sort of growth is called exponential growth. All right. So you know what is a linear growth? That means something which is grows uniformly on every unit of measurement, and exponential means which grows very abruptly. All right. Now, why I am talking about this? Because in all these three geometries, there is something which you can draw on any geometric space. What is that? That's a circle. So for drawing a circle, you don't need anything. You just need a compass and a point, and you can draw a circle. You can draw a circle on the sphere. You can draw a circle on the plane we are living in, and you can draw a circle on this hyperbolic world, on the coral also. But what is the difference between all these three circles? So you draw a circle, you cut the circle at a point, then you measure the length of the curve. That's the perimeter of a circle. And you know that from center to the perimeter, that distance is called the radius of the circle. These are also well-defined notions in all these three geometries. Now, the formula for perimeter of a Euclidean circle, as you all know, is 2 pi r. What does it mean? That means you take two right angles and multiply it by this quantity 2r. So think of pi now as a number which quantify two right angles. All right. Approximately pi has a value which is close to the fraction 22 by 7. But anyway, so the perimeter of a Euclidean circle is 2 pi r. So that means when you increase the radius, the perimeter of the circle grows linearly with r. Now, what is the perimeter of a circle on the sphere? There is a formula for it, which is 2 pi sine function on r. So sine function is a trigonometric function, and 2 pi sine r is the perimeter of the spherical circle. Now, if you know sine function, you can immediately say that this means the perimeter of a spherical circle always lies between minus 2 pi and 2 pi. Now, what about hyperbolic circle? So there is this sine hyperbolic function. So the perimeter of a hyperbolic circle is 2 pi multiplied by the radius when applied by the sine hyperbolic function. Now, if you know this function well, it grows exponentially with r. So the perimeter of a hyperbolic circle grows exponentially with the radius. So these are three differences. These also exhibits the three differences between the three geometries that I have described. So in Euclidean geometry, circles grow linearly with the radius. In spherical geometry, circles are bounded, always bounded, whatever radius you choose. But in hyperbolic geometry, circles grows exponentially with the radius. Now, I hope I have been able to give you a feeling of these three different kind of geometries. Now you look at our entire universe. Take any surface on the universe. Take any surface. Now draw a triangle on it. You draw a triangle, all right, and see what sort of geometry it has. If the triangles are like Euclidean triangle, then the surface is flat. If the triangles are pat, that means the sum of the angles is greater than pi, then the surface is spherical. And if the triangles are thin, then the surface is hyperbolic, like our corals. And it is a deep fact in mathematics that you take any nice surface in this universe, it is locally modeled on either of these three geometries. That means the surface can be obtained by pieces which you can cut and paste, and each piece belongs to one of these three geometries. So this is a deep application of the three geometries, and it also tells you how much curved a surface can be. But I have not mentioned that. That's it. Yeah, but what I'm trying to say that when you live on this geometry, the underlying roads you will feel how much curved they are. Like on the sphere, you can see they are curved like this. On the flat world, it's flat, and on the hyperbolic world, they are slightly concave. All right. So with this, I will now say that scala hobe. That means it's time to play a game. And you know, this scala hobe was a very famous slogan. But here also now I have written this slogan because we will indeed play a game now. So I will, before I go to questions, where is the Zoom link for me? So let me stop sharing first. Yeah, I stop sharing and I will share something else. Just give me 1 minute because we will now play a game which I am sure you will enjoy. So this game is to realize this hyperbolic geometry. So we saw that we have well-defined model for Euclidean geometry, which is a piece of paper, scale, ruler, compass. We have a model for spherical geometry, which is a football. You can take a football and try to draw great circles there, and you can see spherical geometry. But what about hyperbolic geometry? It's indeed very complicated, right? Because you have to cut this paper in terms of the disk. You have to draw semicircles, which are orthogonal to the boundary, etc. But now, by the use of computer, you can play non-Euclidean geometry on the computer. So there is this website called non-Euclid, which I have presented in front of the screen. Now what you can do, you can say, take 2 points here. So maybe I want to move point. So let me first draw a line segment. So you see, yeah. So I am drawing a line segment here. You see, I take a point here, and then I am drawing a line segment here. So these are hyperbolic lines. Now what about lines from boundary to boundary? You see, it is always a semicircle orthogonal to the boundary. Or if you take diametrically opposite point, then it's diametric. It's the diameter. Those are the lines. Now you can clear everything. Now I want to draw a circle. I want to especially draw the circle because this will also tell you what is the difference between the Euclidean circle and the hyperbolic circle. I take a point. Now this is a circle. It's nice, right? It's a circle. I make it bigger. It's like Euclidean circle, no difference. But now I take a line near the boundary. This is a circle, right? Now I take it, okay, maybe I take here. Now you see, this is the center of my circle, and this is the radius. So you can, I am drawing, so the measurement between A and B is 1.49 unit, and I take the measurement between A and I take a point here. Okay, so now I measure the distance between A and these points. C. You see, this is 1.49. So the hyperbolic distance, as you have already seen, though the circle looks similar, but what really is different is the location of the center on the hyperbolic space and the radius. So here my compass has to be such that it measures the hyperbolic distance. And you cannot draw a hyperbolic circle on the hyperbolic plane by your Euclidean compass, because using your Euclidean ruler, this distance between A and C is certainly lesser than the distance between A and B. But when you scale your Euclidean distance by hyperbolic scale, the distance between A and B is same as the distance between A and C. And I have written it there. Now what about measuring angles? Let's measure some angles here. So maybe I clear all, and I again take a 3 point. So I take these 3 points, and then I want to draw a triangle between these 3 points. This, and then I have this. Okay, so this is my triangle, right? Now what I want to measure? I want to measure angle. So look at the angle at these 3 points. How to, you see angle ABC, that is 54.9 degree, angle CBA, that is 54.9 degree, and angle ACB, that is 20 degree. Now if you add the sum of these 3 angles, then you can see that they are definitely less than 180 degree, which is my 2 right angles. This is the details of the triangle. It is also telling you the length of the sides BC, AC and AB, and the angles. And the angle sum is 108.3 degree, and the area, you subtract 108.3 from 180, that's the area, which is 71.7 degree. Alright, so this is the applet that you can play with, and there is this site called non-Euclid. So if you go to google.com, okay, you just search for non-Euclid. That will take you to this website. And there are these many, you can also do animation here. So if I switch off my animation, you can, there are also some inbuilt, pictures like isosceles triangle. You see this ABC, this is the isosceles triangle in the hyperbolic plane, and then parallel lines. You see, you have this line AB, and you have more than one parallel lines passing through C. And in fact, I can draw more. In fact, I can draw more. So like I can draw many more line segments which is passing through P and parallel to N. So you can play with it. So maybe line. I draw a line here passing through P. This is good. So you see how many parallel lines you can draw through C, which is parallel to AB. The answer is you can draw infinitely. So in hyperbolic geometry, given a point P, which is here C, which is not on a given line AB, there are infinitely many lines which passes through P and parallel to it. And you can see it here in this software, online software. All right. And you can also get a small description about different geometric concepts here. So like I clear everything, and then how a rhombus looks like in the this is a hyperbolic rhombus, okay, which is a quadrilateral in which all four sides have equal length. You see, in the here, even though the sides looks different with respect to our usual mindset, but with respect to the hyperbolic eye, all these four sides have equal length. All right, and so triangle, median, and centroid. So a median of a triangle is a line segment joining a vertex to the midpoint of the opposite edge. So y is the midpoint of the edge AC. All right. So you can play with it and you can try to see the difference between Euclidean geometry and hyperbolic geometry. You can actually feel the difference and you can actually explore yourself by playing with this approach. With that, I would like to thank you for your attention. Thank you.
Thank you, Krishnendu. As you said, there are some questions, but I think some of the questions are already answered by your showing the visualizations of hyperbolic geometry objects. So I think what we will do is probably
Yeah, one question is, can you give some reference books?
Yeah.
Okay. So at this level, there is this book by Edwin Moyes. So, this is a good book, Edwin Moyes. And what are the other books? Okay, there is another book that you can try to look into. It's called Harold Wolf. The name of the book is Non-Euclidean Theorem. Okay, I'm writing it in the chat box. Okay.
Can you share your screen, Krishnendu, so that everybody can see?
No, I am writing it on the chat box.
Oh, chat box. Fine. Good, good.
So chat box, and there are there are many books by sorry, where is the Zoom? Here. Okay, so there are many books by Coxeter, classical books of geometry. Okay, now if you are an undergraduate student, then there is a recent book by S. Kumaresan. It's called Geometry, which is a good book. I hope the spelling is correct. Okay, so that's a good book. And you can also look at, so there is a classical book Geometry by Fenchel. Okay, but these last two books are for evening PhD students. But the other books are for school children, so the school students can read them nicely. Okay, these are some books that probably one can look into. Okay, yeah. So I think these are some references. But this book by Edwin Moyes and the one by Harold Wolf, those are nicely written, and a school student can understand them while reading them. A school student who has a knowledge of geometry and a little bit of trigonometry.
Any more questions from the participants?
Yeah, they can unmute.
Yeah, then, sure. I think in the meantime, when they're thinking about questions, Krishnendu, let me ask you a question as a school student.
Yeah.
See, normally you gave that example of traveling from Delhi to Sydney, right? But supposing you take 2 points, say 2 stars, how do you
Yeah.
locate a star? Is it again by longitude, latitude, something like that, or how do you find the distance between 2 stars?
Well,
Is it
I
spherical
think
geometry again, or is it something else?
spherical geometry again. I mean, the underlying idea is definitely spherical geometry. Yes.
Okay. Yeah, because
So
one has the basic idea of what is meridians, what are the longitudes or latitudes. We can pinpoint longitude, latitude of various places and find out the
yeah.
stars for that. But for the stars, is it something similar?
Yeah. So it's a spherical geometry again. I mean, you look at the
Okay.
location of the star and you look at the, either latitude or longitude are much more modern concepts, I think. Classical astronomers, they don't use latitude or longitude in those things, right? Because I think it's in the modern geography they have introduced latitude or longitude, but classical astronomers used similar concepts to
Okay.
measure location of two stars. I mean, in spherical geometry, there are several measurements that is available throughout history. The one I gave here is much more modern, where you assume that there is a center of the earth. But classical astronomers or classical sailors, they did not knew that there is a center of the earth, right? So they always used to do it in terms of something on the surface of the earth, or either the horizon or the location of the star with some standardized unit or standardized point on the surface of the earth. So yeah, so I think it's also spherical geometry. So there are, like I gave you one projection, which is a stereographic projection of the sphere. But there are also this Mercator projection and things like that, which use spherical geometry in the background without knowing that it is spherical geometry. And they used it for their practical purposes.
Only one observation that came to my mind, that Poincare disk hyperbolic geometry, that picture is due to a famous Dutch artist called IISER.
Yeah, that's a
I think,
problem with that.
and he did it when there were no computers or anything available, just bare drawings. He could do that Poincare geometry, hyperbolic geometry on the disk. So I think,
So here there is a question that if we take the uppermost and lowermost points as 2 points, then will they have infinitely many lines joining them? No, right? I mean, there will be only two lines joining them. Actually, one line, the great circle, right? Now, if you go from North Pole to South Pole, either you go along this side of the great circle or that side of the great circle.
No,
So on the
for
sphere,
north and south, I mean they're antipodal, right? There are infinitely many. If
no,
these
no.
two
So what is?
points are antipodal points,
Yeah.
then
Oh, so
yeah.
there are there are infinite.
all great circle passing through those points.
Yeah, so it not only north and south pole, but if we get two antipodal points,
Yeah,
there
yeah.
will be infinite lines joining them. Is it correct, sir? Yes. That's what it is correct. Because you can draw many great circles passing through this antipodal. Right.
Anybody has more questions or comments?
Yeah, I just want to ask one question to Professor Rana.
Yeah.
So this non-Euclid software that he has shown, Krishnendu sir,
Yeah.
can we do similar thing in GeoGebra also? Like, or
No, I think mostly GeoGebra is basically Euclidean geometry.
right?
I'm still to see hyperbolic geometry or spherical geometry appearing somewhere. Maybe
Well,
geometry you can do it using GeoGebra, because that is more or less geometry on the sphere.
Yeah.
I don't know about hyperbolic. Yeah, Krishnendu, you were saying something?
so the comment that, if you take two antipodal points, whether the line joining them, there are infinitely many or not. All right. No, I don't think there are infinitely many, right? There is only one great circle that you can join North Pole and South Pole. Yeah? So that's a unique line. Now you can either go from here to here or you can go from here to here. What are the other lines that you were seeing? Is not clear to me.
No,
There is
for
a
a
unique great. There is a unique great circle
no.
given to point.
If it's not antipodal, then what you are saying is correct. But if they're antipodal, so their distance is pi. Right?
Yeah, definitely right.
Then, I mean, we can see, right? There are many great circles passing through.
No, I
those
think I was wondering that
Yeah. So
given
that's
any
the question, right?
given any 2 points on the sphere, there is only one great circle which passes through them, right?
In case
Yeah.
they are not antipodal, then only one.
Okay. Yeah,
No, but
all latitudes are probably great circles, right? Passing through those antipodal points.
latitudes are great circles.
Latitudes are great circles, all of them passing through the two antipodal points.
Yeah.
Not circles. Yeah.
There is one question from somebody in the saying any Indian context to the geometries, these geometries. Some
Say it again.
kind of we can claim that okay, some of our mathematicians also had,
Oh, there is
because
no
we did.
volume for me.
Hello.
Say it again. Yeah. Tell me.
We had also done a great job of astronomy. Our earlier people, we had great astronomers. Did they have
Yeah.
anything to have anything to do with spherical geometry or any idea about
Well,
hyperbolic?
I mean, I know that the geometric study for Euclidean geometry was definitely done in the Indian context. So there are these Sulva Sutras. So that's the doctrine of geometric study by ancient Indian mathematicians. I, uh, I think for spherical geometry also there must be some account because the astronomy was sort of there was a rich school of astronomy in classical in ancient India, and if you look at this, for example, even in this in the last maybe 2000 years, if you see the Indian history, so there are many architectures in India where you will see touch of either Euclidean or spherical geometry. Okay, but this non-Euclidean, I mean, the hyperbolic geometry, I do not think that there are anything in the Indian context in terms of hyperbolic geometry. Yeah. Yeah, I hope.
Yeah.
Yeah.
I think I also don't think so, but I think probably more search and research may be required to find out in the ancient Indian mathematical history whether any such lineage is there or not. So,
Right.
more questions from anybody else?
Yeah, but let me just clarify this question again that are Arthatrana Suna to everyone. So the answer is yes. What you are saying is correct.
Okay.
Like longitudes are great circles passing through North Pole and South Pole.
So I think seems no more questions either from the audience or from us. So let me formally thank you again for coming over and giving us that we can look for one God or many gods in various. It's a view of looking at things, but
Yeah.
eventually it is what satisfies you that is important. And also, I think your talk also illustrated to me a very good thing that um, normally our students and teachers don't have the habit of asking questions. So if you ask in the 5 postulates, if I don't have this postulate, then what will happen?
Right.
If this does not happen, in general, that attitude of asking questions, we take it for granted what is given. We don't seem to ask questions. So it is mathematics developed by only asking relevant questions and finding suitable answers. Yeah.
Yeah.
Okay. Yeah. Want to say something?
No, it's
Okay.
fine.
Yeah. Okay. So thank you very much once again. And thank you all for joining. And thank you all those who contributed to our this effort. And take care. Be safe. And
Thank you for your thank you for the invitation. I really enjoyed.
Thank you. Thank you.
our pleasure also. Thank you.
Thank you.
Bye bye.